Stars, some of the most fascinating things in the universe. Every second, most stars give off millions and billions of times more energy than a hydrogen bomb. But even among the many stars of our universe, there are some even more out of this world. Despite how interesting stars can be in life, the most fascinating parts happen only when they die. When a star that is 8 times more massive than our sun dies, it goes supernova, an explosion so bright that it outshines galaxies. What is left behind varies, but if the conditions are right, you get a neutron star. Neutron stars are the densest objects in the universe, second only to black holes. But why are they like this? In a normal star, gravity is balanced by heat. Neutron stars, however, are formed during the moments of greatest compression of a supernova, when unimaginable amounts of matter are compressed into an extremely tiny area. Under these conditions, the density of the core is at a peak, resulting in gravity too strong for heat to balance. Instead, the particles inside the neutron star start to physically bump into each other, halting collapse. When the remains of a star blast off, the still compressed core remains, a neutron star. Let's look inside the neutron star. On the surface exists an atmosphere as thick as hair, with currents ruled by the star's magnetic field. The outer crust is theorized to be a shell comprised of pure iron. Under that, we will run into the so-called nuclear pasta, the material that makes up the inner crust of neutron stars. First is the Nachi phase, where nuclei are packed so tightly that they touch one another, forming little blobs. This will be followed by the spaghetti phase, where these blobs connect to form long chains, and then the lasagna phase, where chains merge into sheets. After pasta comes antipasta. In the anti-spaghetti, the sheets fold in on themselves and turn to hollow tubes. In the Nachi phase, these tubes split off into hollow bubbles. Finally, we reach the core. Scientists are still unsure exactly what it looks like, but many models have been proposed, from a soup of not just neutrons, but more exotic pions and kaons, to quark matter. But that is a discussion for another time. Quarks are the building blocks of hadrons, a category of particles that include protons and neutrons. Protons are made up of 2 up quarks and a down quark that are bonded together, in a neutron with 2 down quarks and an up quark. Under the extreme pressures of neutron stars, protons and electrons fuse, forming neutrons. With even more pressure, however, neutrons themselves break down into quarks. This forms a hyperdense soup of tightly packed quarks, known as a quark-gluon plasma. While we can briefly create these plasmas in particle accelerators, we are not sure if this plasma exists in the cores of neutron stars. This is all just some quirky theory. Strange matter, another proposed idea for the cores of neutron stars. It is a type of quark matter, as mentioned before, and as you can guess, it is really strange. Under particle extreme pressures, when all lower energy are fulfilled, it is possible for transmutation to occur. More specifically, rarely, a down quark can turn into a strange quark. Since strange quarks are heavier than down quarks, this transformation takes up some energy. In exchange, however, an entirely new series of quantum state is freed up. Since the minimum energy level of any new state for down and up quarks are already so high, the ability to access these new lower energy levels can decrease the overall average energy of the system. Matter that contains strange quarks is known as strange matter and is thought to form blobs known as strangelets. These strangelets are known to range from the scale of individual atoms to the scale of meters, at which point they are called strange stars. Our understanding of strange matter suggests that strangelets should be unstable and short-lived at small scales, but potentially even more stable than ordinary matter at larger scales. Following this theory, any stable strangelet will immediately start consuming everything around it, creating more strange matter. The fact that this hasn't happened yet means that we probably don't have to worry about messy green Armageddon, but then again, there are many things we don't know about this strange, wonderful world.